So now let's move on to the next topic, which is the description. Let's understand how these four topics or four blocks are working. And to try to understand this, let's think about this biological example. Imagine that we have three genomes, right? We can have 3,000-4,000 of genomes. And the only information that we have about these genomes is that they have protein coding genes. So the information that we have is that they have these genes, and these genes code for these proteins. And that's the only thing we know about these genomes. So when we put these genomes that we don't know anything about them into MEBS, the first thing that MEBS is going to do is going to identify the proteins that are involved in a specific cycles. Let's think about different colors, and those different colors are the proteins that are involved in sulfur, methane, nitrogen, and this was iron, sorry. So that's the first thing. MEBS is going to characterize all those proteins that are involved in those specific cycles, and the rest we're not going to care. We just care about those that are involved in those cycles, right? So the next thing that MEBS is going to do, MEBS is going to compare those proteins, each one of them, and it's going to compare with a pre-computed database with the relative entropies. This is already a built-in function that has been computed in MEBS, and I'm going to show you later. But just keep in mind that for each of the proteins, we have a specific pre-computed relative entropies. And just to have an idea, the closer to 1 or greater than 1 means that this value is informative, and negative values are not informative. So for each one of these proteins, we have a specific relative entropies pre-computed. And now what we're going to do is imagine we have a specific enzymes. And then we compare this with the database. Now, the next step that MEBS is going to do, it's going to kind of sort those out. And considering the relative entropy, imagine for genome A, we have 8 proteins involved in a sulfur cycle. For genome B, we have just 1, which is the one in yellow. And for genome C, we have just 1, right? So now with this number, what we do is that for each one of those proteins, we sum the relative entropy of each one of these, and then we get the score. This is very important just to think about how the score works, because that makes it very efficient and improves the computing power, because it has already a pre-stored database with pre-computed entropies, and it's going to sum all of those. This doesn't mean that all of the genomes that you have are going to have a similar entropy. As every time I explain this, so imagine that you have a genome that is a sulfate reducer. That sulfate reducer organism is going to have sulfate reduction genes. Those genes can have negative or positive entropies. That doesn't mean that just because it's a sulfate reducer, it's going to have all of the enzymes for the sulfur cycle. And we're going to explain that later. But just keep in mind how this works. Genomes, pre-computed database, identify those that are involved in a pathway, check with the database of pre-computed entropies, and generate the score, right? So the first thing we did in order to get an idea, the first case of study to test the applicability of the score, we really didn't know if this was going to work. This was kind of the main idea. Now we wanted to test this. We wanted to see whether this idea of the mathematical model and the biological information was able to really capture a biogeochemical cycle. And we wanted to focus on this because when I started my PhD in Cuatro Ciénegas in Coahuila, we were interested in characterizing the sulfur cycle. But there was not a lot of information about the sulfur cycle, and I didn't want to just to look at the specific genes that were previously described. I wanted to characterize the entire metabolic machinery of the sulfur cycle. And the sulfur cycle is one of the most complex because of the redox states of sulfur, and was one of the most unexplored cycles at that time. So this is just an idea of how a biogeochemical cycle works, is the organic and inorganic forms of one specific element that form life on Earth. And so we wanted to characterize that, right? And so we wanted to see whether we were able to capture all these processes on Earth with the mathematical model. So at that time, what was the available data that we had? We had databases, we have organisms involved in the sulfur cycle, we had proteins, we have large-scale data sets. And now the next thing was, okay, can we integrate this into the relative entropy? So the first thing we did is to obtain or kind of compile a big database of all of the organisms that are involved in the sulfur cycle. What we did was basically all of the different compounds of sulfur cycle on Earth, all of the organisms that were using or metabolizing those compounds, and then analyze their metabolism. And then we integrate all of this information into this cell that has all the organic compounds of sulfur cycle that we can see in orange colors, and then all of the inorganic reactions. And then here we see the main crossing points. But the important thing is that we were able kind of compiling, we use databases, we use Keck, Metasite, public information in order to compile this, because we wanted to make sure that we kind of have all of the information available at that time. We also, at that time, I mean, I'm talking about 2016, there were 4,000 genomes. Now, obviously, we have many, many more. And non-redundant, we wanted to have a non-redundant data set, because this is very important, because out of this 4,000, many were, for example, E. coli. We have hundreds of genomes from E. coli. We didn't want that. We wanted to have a very good representation of all of the genomes that were available at that time. So that was the genomic data set. And then, oh my God, and then the metagenomes that were available at that time, I use MGRS. And so I had to put 4 conditions in order to use the metagenomes that were publicly available, that had associated metadata. And some of you that work with metagenomics, you know that this sometimes is not as easy as it might seem to have the ecological data associated with that metagenome. I wanted to focus on the ones that were clearly metagenomes with identifiable, well-defined environments, and I got rid of all the ones that were host associated. So that was all of the information, right? So we put all of that into the model, and then we wanted to test that. And so when we generate the sulfur score, we wanted to test the performance. So first of all, we score all of the genomes. We had 2,000 genomes, and then we generate the score for those 2,000 genomes. As we can see here, this is the score in bits, and this is the metabolic capability. Basically, what I did is I divided all of the genomes based on their score. These are the organisms that are non-sulfur. Here are the sulfur unrecognized genomes, and here are the ones that I know for sure that are sulfur cycle, because those were the ones that had physiological and metabolic evidence that were involved in sulfur, either using it as a source of energy, etc. And then we realized that there were several genomes that had a very high score that I didn't consider at first. And then when I look at the environments of those genomes, I realized that many of them were obtained from sulfur environments. Many of them were metagenome assembled genomes. Many of them were obtained from the deep sea. So this was just a way in that we screen all the data, and then we realized from just having this high scores what those genomes might be. And then what we did is to see how accurate we were by computing the score, how accurate the score is. In this case, the sulfur score. And this graph is a ROC curve, or receiving operating characteristic. And this graph is a plot to use the ability of a classifier. And the ability of a classifier is just showing the trade-off between sensitivity, which is true positive rates, and specificity, which is 1 minus false positive rates. Just to kind of highlight a perfect classification in this type of curve, it's in here. And it just shows how accurate you are. Imagine that if you have values here, that means that your classification is by random, it's random. But if you go away from that, it means that you are being more accurate. And in order to have an accuracy value, which is an accuracy value, it's 1. Imagine it's the area under the curve, and it's the probability that the classifier will rank randomly positive instances higher than randomly instances. So how accurate we were. And we obtained an accuracy of 0.98, which is very good, which means that the classification has been done correctly. And so we did that in the genomic data set. And now we wanted to see whether we were able to have this classification in metagenomes, right? And so here I am showing you the distribution of all the metagenomes that I analyzed. I analyzed like 1,000 metagenomes at that time. And here I'm showing you in blue the ones that have a higher sulfur score, which is basically a view of the sulfur cycle across the globe. And when we look at the environments associated with this metagenomes, we can see that we can see here the type of environments. And then I analyzed all of the ones that were above the 95th percentile to kind of see whether those were associated with sulfur environments. And indeed, they were associated with sulfur environments. So that was the first case of study to when we came up with MEBS. We tried with the sulfur cycle, and then I was interested in characterizing the other cycles, right? So now, as you remember from this graph, now I gave you the example of the sulfur score, but now MEBS has this pre-computed entropy values from the rest of the cycles. We have sulfur, nitrogen, oxygen, methane, and iron. And here we have the entropies of all of those BFAMs. We have 112 for sulfur, 120, 60, 76, and so on. And here I'm showing you the different values in the fragmented data set. In the fragmented data set, what we did is we fragment in different sizes the genomes, and we fragmented 2,000 genomes, because at that time, when we were analyzing the metagenomes were short. So many of them were having the size of 30, 60 amino acids long. And that's why we fragmented this in order to see whether the entropies were different at different lengths. That is basically that what it's already incorporated. Here I am showing you the accuracy of the other cycles that are in MEBS. And this is something that I've been preparing, but it's already in MEBS. And so as we can see, MEBS is just basically having genomes, metagenomes, or maps, assemble them, have the protein coding genes, meaning the amino acids, put them, and then score them whether they are informative or not. And with this, we can do a lot of things. And this is just an idea of how I see MEBS in the future. I would love to incorporate more databases. I would love to incorporate, I don't know, databases of related with bioremediation, with antibiotics, biosynthesis, extreme environments, etc. Right now, I just have, it's now the cycles, but this is kind of thinking about the future.